Can you hear me? Sorry for the mishap. It's been taking a while here to get connected. Let me share my screen. Hopefully you can see this. Here we go. I'm Alex Babagnou, CTO at 3Edges, and we're going to talk today about using graphs for authorization. Now, I come from the identity and access management world, so not from the graph world. Nevertheless, I've been speaking about and evangelizing use of graphs for identity for quite a while now. So before getting started, I just wanted to go through a quick background about identity and access management. If you're an identity professional and you're looking at this, this is for our graph practitioner friends, just to make sure we're on the same page. So we'll focus today on mainly the transactional aspects of identity and access management. And those have two flavors. One is authentication, and the other is authorization. So authentication is essentially like the gate to your castle. It's the front door where you need to present your credentials in order to enter. Once you identify someone, then you let them in. Simple as that. Authorization happens once you enter the castle. So it drives what you have access to once you're in there. Which staircases you can access, which doors you can open. And in particular, the thing we want to avoid here, the thing we want to prevent is this thief here that has managed to go past our front gate. We want to prevent that person to actually steal too many things in there. So how do we do this? Here is a quick 101 on authorization theory, the canonical way, if you will. Back in 2003, so about 20 years ago, there was a specification called ZACML, or Extensible Access Control Markup Language, and that defined a way to do authorization using attributes. And that way is called attribute-based access control. What it is, it's basically using a set of policies made of rules, and these rules use attributes of the subject, of the resource, or environmental conditions such as time of day or location, in order to compute in real time a decision, a grant or denied decision. So essentially, these systems were built as follows. This is kind of a high-level architecture of such authorization systems. If you have a record you're trying to protect here on this side here, these authorization systems were made of four main components. A policy enforcement point, a PEP, which acts like a proxy that you put in front of the thing you're trying to protect. This PEP catches all the requests that are made to the resource and forwards them to a PDP, a policy decision point. This PDP evaluates access policies that it gets from a PAP, a policy administration point, essentially a store for your policies, and also can look at some data through a PIP, a policy information point, to retrieve extra attributes. And using those policies and data, the PDP computes a decision, returns the decision to the PEP, which grants or not access to the resource. Simple as that. Now, as developers, if I were to ask you if you're using this methodology or this architecture, you may comment on the chat, but I'm pretty sure the answer will be no. And we'll have a look at the implications of all that today. So to summarize, authorization is the way to ensure that subjects have access to the resources they are entitled to, no more and no less. But as a more pervasive thing nowadays, one of the main things we want to prevent is data breaches. So nowadays, data breaches are on the rise. There are even now crime-as-a-service offerings out there. You can hire criminals that have full-fledged organizations that would help you to breach pretty much any system. And the reason why these systems can all be breachable is because 88% of data breaches target identity. And you can see that also in the fact that there is over 100% increase in stolen credentials out there in underground markets. You can see that in the fact that the breakout time has decreased from 90 minutes down to 84 minutes nowadays. What that means is what the breakout time is the time that it takes for malware or spyware to spread from the system it infected to other systems. This also gives you a time frame that you have in order to react to those breaches. So as you can see, if this happens on a Saturday night and you're not there, then it might be already too late. So there's a sense of urgency in those breaches that we need to take into account when we do authorization as well. As a case in point, if you look at the MGM Casinos breach that happened just about a month ago, what happened there is that somebody called the MGM Casino employee support and just asked for a password reset. That's it. That's all it took to breach MGM Casinos. The consequences of that simple breach was they lost about 6 terabytes of data right away. They lost about $84 million in revenue because of the time they were out, plus about $1 million per day for cash flow. Plus they had to pay from $30 to $50 million in ransom. And of course, the hit to the reputation and any ensuing lawsuits. And we're not quite sure how to quantify that. So the consequences of a data breach can be quite dire. So what are the methods that those attackers use nowadays? They're quite telling. I mean, we know about phishing, obviously. We know about social engineering, which was one of the examples I just cited. But there's also something called MFA fatigue. Now, multi-factor authentication is a good way to try and prevent breaches, but there's fatigue. MFA comes at a high friction cost, so users are not really liking it, so they don't want to use it. And when they do, there are even techniques to steal their recovery codes or send them push notifications incessantly until they click approve. So even MFA is not a foolproof technique to prevent data breaches. So as you can see, the root cause, the main problem that we're facing here is humans. We are all humans and we make errors. We make errors in judgment, and there's no software out there that will prevent that. Unless you install something in my mind that prevents me from moving my hands, what can we do? Well, the solution is actually a newish philosophy in the field of identity and access management. It's called zero trust. And essentially, it's a paradigm where we never trust anything and we always verify. Pretty simple, but that means in particular that we should not trust even authenticated subjects or identities. To give you an idea of what that looks like from an organizational standpoint, this is the NIST reference architecture for zero trust. You can find this publication under the number 800-207, whatever. But you will notice that the central piece of this zero trust infrastructure is this policy decision point and this policy enforcement point. This is essentially an authorization service, as we've seen. So authorization is pretty much at the very center of everything here for the new organizations. So we'll talk about the other pieces of this picture in a little bit, but we'll get back. So authorization then. How is this currently enforced? And now what I'll show you here applies to all kinds of organizations. They may be public or private in all verticals. And I've been about 10 years in the field as a IAM consultant, and I've seen that in pretty much every organization I've seen, including IoT. Anyway, so the way it usually unravels is as follows. An organization has a set of employees, of course. They may also have a set of external users, such as contractors. If the organization is a higher education university, for example, they may have all kinds of different types of users, like faculty members, students, staff, etc. All of these users need to access internal resources, right? Such as apps, data, devices, APIs, various systems, cloud environments, and off-the-shelf software. Great. Now, these internal resources need also to sometimes access external APIs, and of course, external apps. And of course, we have our customers, which should be able to access our products and services. Some of the internal users may also need to access those, just at least to provide support, right? And now, over time, organizations typically partner with each other. So we have now partnerships. Now, note that this applies also to acquisitions, for example. So partnerships have the partners have their own employees that can access the partner services. They have partner customers, and all of these people and all of these communities need to interact with each other in sometimes very complex ways. So as an application developer, as a graph practitioner, what has been your main way to solve this complexity problem so far? Still very much in use in about 90% of organizations out there. Role-based access control, RBAC. You use roles to solve all these authorization problems. It's kind of like the solution fits all solution here. And I'm here to tell you that this is bad. This is bad because it leads to a very prevalent problem that 90% of, or probably more actually, organizations have nowadays with roles, and that is role explosion. Over time, because of all these new things and all these things that you add to your environment, you need to create more and more roles to make sense of your authorization. After a while, you have so many roles that you can't tell for sure who has access to what. And this is a big problem. During a data breach, for example, you can't tell what the impact of a breach is. If your user that is being compromised has access to too many systems, well, guess what? You will lose more data. So it is quite important to restrict access as much as possible. And that's really hard to do with roles, or not impossible. Actually, I've actually seen the latest case in point, an organization that has 30,000 roles. How do you make sense of that? So instead of using roles, we need to use something else, something called dynamic authorization. So here we need to differentiate between static and dynamic authorization. So static organization is, for example, roles. Here's an example of an LDAP group, which is often used for role-based access control. Here's a group, and as you can see, in static authorization, we define sets or buckets, and in there we list a number of members. So for example, here we have a role with a number of unique members. I've personally seen roles that have 10,000 users in them. Pretty unwieldy. Another example is access control lists, which is what you see in Unix systems, or tuples. We'll get back to tuples. On the other side, dynamic authorization uses rules, and it's what I was talking about earlier. You need to use rules. What's the advantage here is that you may have a small number of rules that can replace a huge number of static buckets that you have. Compare, for example, 100 rules to 30,000 rules. And it's easier to centralize the management of these rules, whereas managing 30,000 rules is not impossible for anyone. So dynamic authorization is what we should do instead of role-based access control. Given that, well, there are essentially two ways to do it. One is not to use graphs, and one is to use graphs. And that's what we're going to talk about today at last. So how do you use your own graphs for authorization? Now, there's various ways to do that, but back in 2019, it was something pivotal that happened in our space. It's called fine-grained authorization, or FGA. It all started with the publication by Google of their paper called Google's Consistent Global Authorization System, which they titled Zanzibar for a reason that still escapes me. Anyway, in that paper, Google just described the authorization system that they implemented to solve all their authorization problems, from Google Doc all the way to Google Cloud. So at the root of this system is the concept of a tuple. A tuple is a simple string, as follows, that relates a user to an object. What this string means is that the user can access the object with this, and the type of access is provided by the nature of this relationship. You can see here. Now this is called FGA, because fine-grained authorization, because the object itself can, in theory, be as granular as you need be. As you need it to be. It could be down to a bit of data if that's what you need. Now, some people have noticed that this could be represented as a graph, and indeed it can. Now, you're a graph audience, so you're probably familiar with RDF. So as you can see, Google kind of took the idea of a triple and made it their own sauce. Now, those same people that have remarked that we could express a tuple as a graph also mentioned relationship-based access control as this type of access control. Now, also, that term relationship-based access control, or Reback, was actually coined in 2007, but that's another story. Anyway, using Google Zanzibar, here's an example. On the left here, you have some tuples and what they mean. For example, here, user number 10 is an owner of a doc called README. User number 11 is a member of group engineering. Members of group engineering are viewers of doc README, and doc README is in folder A. As I mentioned, you can express this as a graph, and here it is. Here's a graph representation of the same tuples. You being graph people, you can already tell which representation is the easiest to use and to manipulate. But surprisingly, FGA practitioners, and I've talked to a few, don't look at the graph at all. It's kind of a neat side effect, but they really look at the tuple strings, which is quite interesting. So then let's talk now about Reback, relationship-based access control. What I mean by that is true Reback. True Reback is when you use a graph as opposed to tuples. So here's an example of how you could use Reback to express role-based access control. That's just a simple example because everybody understands roles. So here's a graph model, a schema, if you will. In this model, we've expressed RBAC. Users may have roles. Roles may be part of a hierarchy. A role may grant a permission over an object. We're protecting the object here. So Reback is all about finding the path between the subject or the user and the thing we're protecting, the object in this case. So if we find a path in the data between those two, then we grant access. Here's a simple example. Here's some data that complies to that schema. We have 3 users, and we have a couple of objects we're protecting, an HR database and an HR application. We have a couple of roles, an admin role and an HR role. So using Reback, let's try to answer this question. What does user Janice have access to? So as I mentioned in Reback, we follow the path between the user and the objects. And if we find a path, we grant access. So here, starting from Janice, we have a couple of paths. Therefore, Janice has access to these 2 objects. She can access the HR database thanks to the admin role and the HR apps thanks to the HR role. Pretty simple, right? Now, user Bob down here, well, there's only one path that can satisfy Bob's access here, and that goes through the HR role, meaning that Bob only has access to the HR app. Pretty simple. Now, if we were to compare real quick FGA and Reback, the main difference here is that FGA tuples are stored in typically a SQL database or some kind of a homegrown database, basically not a graph database, whereas true Reback uses a pure graph database. Of course, one of the main differences is path traversal, where we just need one input-output operation, and we let the database figure out the path. Thank you, Neo4j. On the other hand, on the FGA side, well, we actually need a couple of IOs here in order to figure out our access control. This becomes interesting with a long path traversal like that, where in this particular case, FGA would require 6 IOs or maybe 5 joins. It gets tricky at that point. So another way to use graphs for authorization is to use knowledge-based access control. Very fashionable these days. The idea here is to use a knowledge graph in order to derive your access control. So it's essentially Reback, true Reback, using a knowledge graph. What is a knowledge graph? Well, it's a graph with an ontology. An ontology is a classification scheme that describes the categories of a particular domain and the relationships between them. So if you have your graph data and you know your graph schema or in your graph model, essentially you have your ontology. So now you can ask really clever questions to your access graph, right? You can do semantic reasoning, embeddings, and all the cool stuff that you can do with knowledge graphs. In particular, you can answer questions such as, what resources can user A access? We've seen that. Or what users can access resource R? Or users that can access resource R can also access resource T. Or maybe something like user use access is atypical. So it starts to get really interesting here. Now, one last methodology I want to share with you for graphs for access control is NGAC, Next Generation Access Control. NGAC is actually a standard. It's an ANSI standard that was first published in 2013. References here. So what it provides, it's an architecture and a graph model. So essentially, NGAC is a standardized attribute-based access control with graphs. The architecture of NGAC is pretty reminiscent of that of the XACML ABAC we talked about. It just has a couple of extra components here. A resource access point, which in effect acts as a connector to the resource you're protecting. This kind of limits the access to the resource to those things that are exposed in it. It also may help in discovering those resources. The other element, and this is quite an important one, is this event processing point. Now, in NGAC, the environmental conditions that are date or time-based are expressed as events. So basically, when, say, 4 p.m. happens, this should happen. Or when Sunday happens, this should happen. So any time-based constraints are treated as events. So we use this events processing point to understand those events. But another important aspect here is that we can now, using this EPP, we can now respond to enterprise-wide security events. And this is quite interesting because there's an effort within the OpenID Foundation standardizing body called Shared Signals, which goal is to standardize messages that can be sent within the enterprise or any organization to share events that are security related. So now we have an architecture that enables us to do that. So let's see an example here. Let's look at this attribute-based access control policy example in the banking world. The policy is as follows. Bank tellers can access any bank account located at the branch they work at weekdays during business hours. So how would we go about using our graph to implement that? Here it is. This is the NGAC way. As you can see, we have a graph here. We have a bunch of user nodes and their attributes. We have a bunch of object nodes. These are the things we're trying to protect, as well as their attributes. So in effect, we have a user directed acyclic graph here, as well as an object graph, subgraph, and they're related to each other with these relationships. These relationships are obligations, or they're basically the types of access that is granted to the user to the objects. So there are things like read, update, delete, or whatever custom operations you might have. And the graphs are also connected to each other with these policy rules. So the way this works, to explore the way this works, we'll look at a special algorithm for NGAC called preview, which has been shown to scale well. It's a linear algorithm. So the way preview works is it has 3 main steps. And I'll show you the 3 steps. Before you jump to conclusions, no, it's not heavy on IOs. You can actually load the subgraph or the whole graph in memory and compute everything in there. So it should be pretty fast. So to look at preview, we'll look at an example here. This example will try to determine what user 1 has access to. So the first step of the preview algorithm is to find candidate object nodes. These are nodes that the subject may have access to. So for that, we'll find a path that starts from the user, that goes through those operation relationships all the way to the objects. Here we go. We backtrack all the way to the objects. And now we can find that the user may have CRUD access to potentially these 2 accounts. Second step, starting from the accounts, we want to see what policies these accounts require. So we'll find a path from the objects to the policy nodes. There we go. For account 1, we have 2 policies. One requirement is a role of teller and a branch of branch 1. Similarly, for account number 2, we find a role of teller and a branch of branch 2. Simple. Last step, we need to find which policies the user's attributes satisfy. So for that, we start from the user node and we find a path to the policy nodes. So there we go. And we find that the user has attributes for teller and for branch 1. Comparing everything together, we determine that the user only has access to account 1. Great, we've solved our problem. Well, almost. We need to resolve the time of day thing. So remember, we will use events for that. So when it's 4 p.m., the only thing we need to do here is delete this relationship in real time. And when it's 9 a.m. the next day, we can reestablish this relationship. So toggling this relationship, in effect, removes access or not to the account. Using events like that can also be super useful because we can now react to any type of security event that happen in real time in the enterprise. So back to our zero trust architecture. To summarize, if you have your graph where you have your policies and your identities, then of course you can use it for your policy engine, but you can also use it for threat intelligence, right? You can use it for data access policies. You can use it for identity management. And you can also use it for your compliance, because compliance requires you to make sure that you can prove that accesses of the people. It's much easier to do in a graph than to do any other way, really. And you probably know that. Okay, great. So now what? What are the best practices for developers? Well, there are things you should probably stop doing right now. Please stop writing your own authorization source. I know it's very tempting to build your own little authorization in your app, but as we've seen with roles, it leads to all kinds of problems. In particular, I mean, you should probably not do it if you're not exactly sure what you're doing, really. And also, please stop using roles. We've seen the problems with that. And I know it's hard because everybody tells you now with the new GraphQL features, you can use roles in this and that way. Really hard to do, but please stop doing it. Instead, use external dynamic authorization platforms. These platforms are made by people that spend their day thinking and doing authorization. So you can just focus on your business needs or on your analytics and delegate that authorization stuff, to these platforms. These allow you to centralize your access policies. And the benefits of that is that you can now tell who has access to what at any time. And you can use your own graph. One of the benefits of NGAC, you may have seen when I showed you that graph model, is that you can take your existing graph and just add these policy nodes and these relationships in there. And essentially, that's all you need. There's no special language you need to learn. As long as you model your policies the way I showed, any NGAC compliant authorization engine should be able to understand it. So you can totally reuse your own graph. The benefits: centralized access control, much faster development. You can just offload all this authorization business. And of course, compliance, because now it's really easy to prove that the right accesses are granted all the time. So how to do it? Well, I did this pretty fancy but maybe useless flowchart here. Essentially, if you have an app, you can use a policy enforcement point or make calls to this external system. If you have a GraphQL API, you should probably use these new fancy annotations and make calls to this external system from there. And anything else should use maybe those direct REST or not REST calls. That's it. That's all I had for you today. If you have any questions, feel free to ask me now. I'll check out the questions in the comments here.